In this video, we're going to do a bunch of different practice problems that just highlight some of the things we talked about in the previous video, dealing with the pre-calculus review, looking forward to section 1.7 in calculus material. So first, let's talk about rational functions and the idea of asymptotes. So for the following two functions, find asymptotes, that's both vertical and horizontal, of the following functions. So for vertical asymptotes, the idea is to set the denominator equal to 0. So this means that we have a vertical asymptote at x equals -2. For the other one, g of x, if we set the denominator equal to 0, x squared minus 4, that's going to give us x squared equals 4, or x equals positive and -2. So in the first one, we have 1 vertical asymptote, and the second we have 2. Note that we could find x-intercepts, doesn't ask in this problem, by setting the numerator equal to 0. So that would be x equals -3/4. On the bottom, it would be 3x plus 1 equals 0, or x equals -1/3. To find horizontal asymptotes, we look at the degree of the top and the bottom separately. For the first one, the degree on the top is 1, and the degree in the bottom is 1. So the horizontal asymptote is going to be y equals the ratio of the leading coefficients 4/1, or y equals 4. The idea here is that as x goes to infinity or -infinity, the dominating functions on the top and the bottom are the 4x and the x. And as the x's cancel out, this function just looks like 4 if we think about just the dominating functions. That's an idea we're going to go over a lot in limits in calculus material. On the bottom here, in the second one, the degree on the bottom is 2 and the degree on the top is 1. So we're going to have a horizontal asymptote at y equals 0. Same idea here is if we look at the top and the bottom dominating functions, the 3x and the x squared, this is just equal to the same as 3/x, which is going to go to 0 as x goes to 0. If we know something about our library of parent functions, our idea of the function 1/x looks something like that. We can use that as to help us with the idea of the function itself. All right, to think about if we graph these functions, what would happen? Let's look at the first one only. We have a vertical asymptote at x equals -2. We have an x-intercept at -3/4. And we have a horizontal asymptote at y equals 4. So the horizontal asymptote is what's going to happen at the ends of the function. So this tells us how this function is going to look, because it has to go through this x-intercept, needs to approach that, needs to approach the vertical asymptote. There's a little bit more work to show that it's going to also be looking like this. You can't have another x-intercept, so it has to stay above the x-axis, but there's a quick sketch of that function. We could do the same for part B, but it's going to cover the same kind of ideas. All right. So what does this mean by horizontal asymptote as well? This means as x goes to infinity, if we're looking at part B here, as x goes to infinity, the y value approaches 0. It's also the same for -infinity as well. As x approaches -infinity, y approaches 0. All right. Now let's think about some algebraic equations. A lot of times we're going to have to solve complicated algebraic equations, and it's going to be necessary that you remember all these facts about trig functions, exponential functions, log functions, as well as all of our basic algebra rules. So here are three kind of complicated equations to solve, and I'm going to bring in a lot of past information in order to solve these things. So the first one, sine cubed plus sine cosine squared equals cosine. There's a lot of different ways we can go about solving this, but how I'm going to do it is I'm going to factor out a sine of theta in the left-hand side, and that's because I will be left with sine squared theta plus cosine squared theta on the left, and then equals cosine theta on the right. And if we remember our trig identities, that sine squared plus cosine squared should ring a huge bell because that whole thing is just equal to 1. And that's going to be an important trig identity to remember. So this whole thing goes down to sine of theta equals cosine theta. And if I want to solve that, it might help to bring all the trig functions over to the other side by dividing by cosine, which would give us this sine over cosine, which is the same as tangent equal to 1. So here is now the big thing. How do we solve tangent theta equal 1? One place to start might be to use the inverse function of tangent. And we get arctangent of 1, which is equal to pi over 4. It's the angle value that gets a tangent value of 1. And then we know something about the period of tangent. We know that it repeats itself every pi. So we know that actually there are more than one answer here. We're going to have pi over 4, 3 pi over 4, 5 pi over 4, on and on and on. And in the other direction as well, we're going to have negative pi over 4. Oh, sorry, not negative pi over 4. Sorry, let me do that again. Sorry. We're going to start with pi over 4. We're going to add pi to that. That'll give us to 5 pi over 4. Add pi to that, we get 9 pi over 4, on and on and on. In the opposite direction, I'm going to have negative 3 pi over 4 and everything past that. So here is a list of all of the angles that satisfy that equation. It may be important that we only look at just the pi over 4. It may be important that we look at something else. It depends on the problem. But that's going to be something that we're going to need to know how to do. All right, a completely different kind of problem, one with an exponential. We have the equation 4e to the 2x minus 5 equals 7. Solve for x. And the idea is just get x by itself. So we're going to start by dividing by 4, which gives us e to the 2x minus 5 equals 7/4. To get rid of the e, we use its inverse. We take the natural log of both sides. The natural log and the e cancel out, and we're left with 2x minus 5 equals natural log of 7/4. Then I'm going to add 5 to both sides. That's going to give me natural log of 7/4 plus 5, and then finally divide by 2. That is natural log of 7/4 plus 5 divided by 2. And note that this is what we call our exact answer. You can plug that in a calculator and get a decimal approximation, but this is what we want, the exact answer, more often than not. All right, dealing with logarithms. Let's see how we can do that. There's going to be two different ways we're going to go about this. One is knowing that log base 2 of 8 is equal to 3. Now, why do we know that? That's because when we think of log base 2 of 8 equals something, we're saying 2 to what power is equal to 8. We might know that 2 to the third power is equal to 8. So that is what a logarithm is asking. What power of the base is equal to the thing in the parentheses? So if I write this as 3 plus log base 2 of 4x equals 3, if I want to get x by itself, it might help to subtract 3. And I'm left with log base 2 of 4x equals 0. To get rid of the log, I'm going to take 2 to the power of both sides. That's the inverse of log base 2. That's going to give me 4x is equal to 2 to the 0. Anything to the 0th power is 1. So we get 4x equals 1, or x is equal to 1/4. Another way to go about that would be to use properties of logs from the beginning. We could write this as log base 2 of 8 times 4x equals 3. You can multiply the inside of logs if you have two logs added together. So take the power of, or 2 to the power of both sides, and we're left with the inside here is 32x equals 2 cubed, which is 8. And either way, we get 1/4. So this is a good example of the more comfortable you are with logarithms, the easier you can solve an equation. Maybe you even have two different opportunities or two different ways or strategies to solve an equation. This whole page is just a good lesson, and the more comfortable we are with trig, exponential, log functions, the better we can answer questions. All right, different kind of question, dealing with graphs now. Let's look at the function negative x plus 1 squared minus 3, and I want to know specifically on what intervals is this function increasing and decreasing. We're going to learn how to do this with calculus later on, but right now we can do it with just the graph of the function. So to graph this function, let's start by graphing our parent function, and that is x squared. And we should know that x squared is our parabola as so. And we have three different function transformations on that parabola. We have this plus 1 on the inside, which is going to move to the left 1 unit. The negative out here is going to reflect over the the x-axis. And the minus 3 is going to move down 3 units. So let's do all those function transformations. If we move to the left 1, we're going to reflect over the x-axis. And then we're going to move down 3 units. And there's a picture of our parabola there. Note that this point right here is -1, -3, that vertex, and there's our function. So if we're asking for what intervals is this function increasing and decreasing, what we are looking for is x values. So this function is increasing on the left-hand side of that parabola. That's when the function is going up as we go from left to right. And that's going to correspond to the x values, -∞ to -1. And when we think about increasing, we're always going to use parentheses. We're not going to include the -1 there. This function is decreasing on the right-hand side of that parabola. That's going to be from -1 to infinity. Note that that -3 didn't actually make a difference in our increasing and decreasing intervals. We got the same thing even just from the first two function transformations. All right, so a quick sketch of the graph. The only point I actually made sure I tracked the whole time was the vertex itself. And then I just knew the basic shape of the graph in order to answer this question. Note that when we talk about on what intervals is something happening, we are always discussing x values. When is the function increasing, decreasing? That's x values. Where is the function increasing, decreasing? That's also x values. All right, something we didn't talk about in the previous video is the idea of function composition. It's going to be something we talk a lot about in this course as well. So let's do a quick example of function composition. So this complicated function, t minus e to the t to the fifth, is the composition of two functions together. So we're going to try to identify what are those two functions. Let's say that right now we have f of g of t. So this is, g is going to be the inside, and f is the outside function. It might be easy to see that the inside function here is going to be my t minus e to the t. And that is inside of the function something to the fifth power. And we're going to write that as t to the fifth power. So let's verify that that's correct. If I have these two functions, and I ask you to find f of g of t, that's like replacing every t in my expression with the entire g of t. So that's going to give me something to the fifth power, and the something is the t minus e to the t. The other way we could do the function composition is g of f of t, which would give me a different function here. I am starting with the t minus e to the t, but instead of having t, I'm going to plug in the t to the fifth. So I get t to the fifth minus e to the t to the fifth, which is a different function entirely than the f of g of t. We're going to have to identify the function composition when we start talking about derivative rules, especially the chain rule. So we're going to be doing things like this shortly. All right, different kind of problem here. Let's say you are given something like square root of e to the 2 natural log of 5 minus 3 natural log of 4. That is a super complicated expression, but you can use some common log rules and algebraic rules to simplify that to a nice number. So let's just see how we could do that. First, we could write this as e to the natural log of, not 2 natural log of 5, but 5 squared. That's the log rule that if you have something multiplied on the inside, it becomes a power. And if you have minus 3 natural log of 4, that's the same as minus natural log of 4 cubed. That's using the power rule of logarithms. That's the power rule of logs. Then we could use the quotient rule of logs, noting that this is the same as e to the natural log of 5 squared over 4 cubed. Because I'm subtracting logarithms, I can bring them together as division. And now, because I have e to the natural log of something, this is from inverse functions, this is equal to the square root of just 5 squared over 4 cubed. There's lots of ways you could deal with this square root, but what I'm going to do is I'm going to write this as square root of, actually let's just call this, square root of 25, and 4 cubed is going to be 4 times 4 times 4, or 64, which is the same as 5/8. So a bunch of algebra and log rules allows us to write this complicated expression as 5/8. One last example here. Given a bunch of different functions, let's determine the left and right end behaviors of the following functions. So the first one is 5x e to the negative 3x. And we can write this maybe as 5x over e to the 3x. Note that x to the negative 1 is the same thing as 1 over x. Okay, that negative exponent means you can put it in the denominator. So here, e to the 3x dominates 5x. So as x gets really big or really, really small in the negative direction, the 5x is not going to make a difference. The e to the 3x is going to dominate. So we're just answering questions about this 1 over e to the 3x. As x goes to infinity, we know that e to the 3x is going to get really big. So one thing we're going to do in calculus a lot is we're going to write things like, this is going to be 1 over a really, really big number, or that's going to be the same thing as going to 0. As x goes to negative infinity, this is knowing properties of e to the x, or e to the 3x. As x goes to negative infinity, e to the x goes to 0. So this is going to be like 1 over a really small number, 1 over 0, which we're going to learn more in calculus, means that we're going off to infinity. Right, this is the most calculus-like problem we've done so far, and we'll get into that a lot more details in the next few sections. All right, for g of x, this is a much easier problem. This is just a polynomial. We have that the leading coefficient is negative. We have that the degree is odd. So that means that our end behaviors are going to look like that, which means that as x goes to infinity, y is going to go to negative infinity. And as x goes to negative infinity, the left end behavior, y is going to go to infinity. Lastly, another kind of function we haven't touched on yet is a piecewise function, a function made up of different pieces. And let's just graph this function to understand what's going on. So it says when x is less than 1, less than or equal to 1, h of x is just equal to the constant function 5. So when x is less than or equal to 1, h is just the constant function 5. When h is greater than 1, or when x is greater than 1, this function will be natural log. So if we graph natural log here, we know that it's going to start at the x-axis when we start at 1, going off to the right. So here's a picture of h of x. So from the graph, we can see that as x goes to infinity, y is going to go to infinity because we know stuff about natural log. It's going to blow up to infinity, albeit very slowly. And as x goes to negative infinity, y is going to go to 5. It's just going to be that constant line all the way around. This last page is a really good example of things that we're going to be showing or doing in calculus when we look at limits at infinity and negative infinity. Answering these questions, especially that first problem A, is going to be something where we look a lot at. We'll go over that idea of 1 over big and 1 over 0 in much more detail in the next few sections. I wanted to say one more time, this is a very brief overview of years of work that you've already done. You will have gaps in your knowledge, and it's expected that you try to tackle those gaps in your knowledge. Please reach out if you have questions, and know that you're going to be expected to know all of this, but it's also expected that you are not experts at this moment with everything.